We often talk about fusion as bottling a star, but that actually understates the problem. To make fusion work on Earth, we don't just have to copy the sun, we have to outperform it. And in science, there's a huge difference between a process that works and a machine that's actually useful. Fusion, the perpetual promise. Fusion power has a reputation. You've probably heard the joke that fusion is 20 or 30 years away, and always will be. Decades of headlines, massive experimental reactors, and bold promises, followed by the quiet reality that none of them power your home yet. That pattern has left a lot of people with a lingering suspicion that fusion might be less a breakthrough waiting to happen and more a scientific mirage. And that skepticism is understandable, though a bit misplaced. For the most part, physicists haven't been promising miracle timelines. What usually happens is a genuine breakthrough occurs, the media overhypes it, and the public is left with the impression that fusion was supposed to arrive any minute now. But early on, there really was a period of understandable overexuberance. After all, nuclear fission progressed astonishingly fast. The first controlled fission reactor, Chicago Pile 1, went critical in 1942. Within a few years, fission bombs had ended a world war, and the first commercial fission reactors followed in the mid-1950s. Fusion seemed like the obvious next step. By the early 1950s, we already knew that fusion powered the sun. Fusion reactions had been achieved in laboratories in the 1930s. In 1952, the first hydrogen bomb demonstrated fusion on a massive scale. Around that same time, multiple fusion reactor concepts were being pursued in parallel. In the United States, Project Sherwood explored magnetic confinement methods like the Z-pinch. In 1951, Lehman Spitzer at Princeton designed the Stellarator, before the hydrogen bomb had even been tested. A few years later in the Soviet Union, the first Tokamaks were built, and by the late 1950s, they were outperforming all of approaches so decisively that most alternatives were set aside. And they were all producing fusion. That early progress made it reasonable, at the time, to think fusion power might only be a couple decades away. It wasn't a reckless claim, it was an optimistic extrapolation from genuine momentum. Fusion has been almost here for most of a century. Governments have spent tens of billions of dollars pursuing it. Some of the smartest engineers and physicists on Earth have devoted entire careers to the problem. Yet we still flip our light switches using coal, gas, fission reactors, wind turbines, and solar panels, not miniature stars. So today, I'm not here to sell you fusion. I'm optimistic about it in the long run, and if we ever make it work commercially, it would be a big deal, but it is not a magic wand. Fusion wouldn't instantly make power free or effortless. I don't have a crystal ball for when or even exactly how it gets there. I am also not here to promise that this time is different. The next reactor will finally change everything. Instead, we're going to do something simpler and hopefully more useful. We're going to explain why fusion is hard, what problems fusion reactors are actually trying to solve, and what people really mean when they talk about practical fusion power. Because the problem with fusion isn't that it doesn't work. The problem is that it isn't working enough. Fusion reactions happen all the time. We've been producing them in laboratories for almost a century. The question has never been whether fusion is physically possible. We see in the sun itself and fusion bombs. The real question is whether it can be made steady, controllable, affordable, and reliable enough to function as an economical power plant rather than a physics experiment. And to understand why that's such a tall order, we need to start with why fusion is so appealing in the first place, why generation after generation keeps coming back to it despite so many false starts. Why fusion is so appealing. At its core, fusion is attractive because it promises something close to an ideal energy source. Fusion releases an extraordinary amount of energy from a very small amount of fuel. When light atomic nuclei fuse together, the resulting nucleus weighs slightly less than the parts that went into it, and that missing mass is released as energy. Even tiny amounts of mass, converted this way, can power cities. We see that in the sheer scale of the equation E equals mc squared. But just as importantly, fusion fuel is incredibly abundant. The most commonly discussed fusion reactions involve forms of hydrogen that can be extracted from ordinary water. In practical terms, fusion does not depend on rare minerals, limited geographic deposits, or fuels controlled by only a handful of countries. If fusion ever becomes practical, energy scarcity should quickly go extinct. Fusion is also appealing because of how it fails. Unlike fission reactors, fusion reactors don't rely on chain reactions. If something goes wrong, if the conditions are not exactly right, the reaction simply stops. The plasma cools, fusion ends, and the system shuts down. There's no equivalent of a runaway reaction driven by physics itself. That does not mean fusion reactors would be risk-free, nor should we ignore the huge improvements in fission reactor design that make them far safer nowadays, but it does mean fusion failure modes are fundamentally different. Fusion tends to fail quietly rather than dramatically. Fusion also avoids one of the largest political and social obstacles facing nuclear fission: long-lived radioactive waste. Fusion does produce radiation, and it can make reactor components radioactive over time, but it doesn't generate the same kind of persistent high-level waste that must be isolated for tens of thousands of years. While we can argue about the actual risks of fission waste versus the perceived ones, fusion sidesteps the political third rail of forever waste. It offers a path to nuclear power without the baggage, provided we don't let a new set of misconceptions about fusion fill the void. But overall, fusion sounds like the perfect solution: powerful, clean, safe, and sustainable. So why aren't we already using it? The short answer is that fusion demands conditions far outside everyday engineering experience, conditions that don't just stretch our technology but push against the limits of what controlled machinery can reliably maintain. It's tempting to think of fusion as simply a matter of heat. After all, the sun runs on fusion and the sun is hot. So if we can make something hot enough, hotter than the sun even, shouldn't fusion take care of itself? That intuition turns out to be deeply misleading. Fusion doesn't care about temperature alone. It cares about density, pressure, confinement time, and stability. It cares about how often particles collide in exactly the right way, and how long those conditions can be maintained without falling apart. The sun gets away with being a very inefficient fusion reactor because it is enormous. Its power output per kilogram is actually quite low, though. Individual protons in the sun's core can drift around for millions of years before they ever participate in a fusion reaction. The sun works not because it burns fast, because it burns patiently, and because gravity does most of the work of holding it together. To put that inefficiency in perspective, it takes on the order of 4,000 tons of the sun to produce a single kilowatt of power, about what you use to run a microwave. 4,000 tons. At that power-to-mass ratio, a modern solar panel would be astonishing. Instead of producing 1 kilowatt, it would be producing tens of thousands of kilowatts, and would still generate a meaningful fraction of a kilowatt under moonlight even. It feels strange to describe the sun as low power, but in this very specific sense, it actually is. And in fact, it's more power dense than many stars, some which produce only a few watts per comparable mass. A fusion reactor on Earth doesn't have that luxury. If fusion is going to be powering civilizations, it has to produce vastly more energy per unit mass than the sun does. It has to release that energy on human timescales, in machines that fit inside buildings, and under conditions we can control precisely. We're not trying to build a star, we're trying to outperform one. And that single requirement, more than any other, explains why fusion has been such a persistent challenge. To understand how we even attempt that, we'd look more closely at what fusion actually is, how it happens, and why simply copying the sun was never going to be enough. What fusion actually is and isn't. To understand why we have to outperform something as huge as the stars themselves, we have to look at what's happening at the scale of tiny little atoms themselves. We used to think of nuclear power in terms of fission, taking a massive unstable atom like uranium and adding neutrons until it splits apart. In a reactor, these are usually low-speed, low-energy connections, fusing to some new and often very temporary isotope, though we call this neutron capture, not fusion. We actually have to slow the neutrons down so they don't just bounce or deflect away. We want them to get stuck in the nucleus, creating a short-lived, unstable product that fissions. We then harvest the heat released as those fragments and neutrons bang around in the moderator like water. Real fusion is the opposite. It's taking the smallest, simplest atoms of the universe, usually isotopes of hydrogen, and forcing them together at incredibly high speeds to form something heavier like helium. When those nuclei fuse, the new, larger nucleus has a slightly lower total mass and energy than the parts that formed it. That leftover excess is what we harvest for power. But when we're trying to stick these smaller nuclei together, we run into a problem that doesn't exist for neutrons: charge. Every atomic nucleus has a positive charge, and positive charge repel each other. This is the Coulomb barrier. Think of it like trying to push two powerful magnets together at North Pole to North Pole. Because of the inverse square law, the closer they get, the harder they push back. To get them to fuse, you have to overcome that repulsion, so you get close enough for the strong nuclear force to take over. The strong nuclear force is around 100 times stronger than the electromagnetic force, but it has no range. It's like Velcro or sticky glue. In fact, we call the particles that carry it gluons, but it only works when the nuclei are essentially touching. If you can push them across that finish line, the strong force snaps them together and releases that massive burst of energy. If you don't, they just bounce off and fly away. This is why fusion isn't a chain reaction like fission. You can't just start a fire and walk away. You have to manually force every single collision, millions of times a second, against a force that's trying to push your fuel apart. The sun is hot, and also a terrible reactor. This brings us back to our friend, the sun. We often hear what we need is sun-level heat to make that fusion work. That's actually a massive understatement. The core of the sun is roughly 15 million degrees Celsius. That sounds like a lot, but for a proton, it's actually quite chilly. At that temperature, most protons simply aren't moving fast enough to overcome their mutual repulsion. They just bounce off each other over and over again for millions of years. All that mass is great for keeping up the pressure and for insulating that heat so it stays in the core. Very little actually leaks out. The sun only works because it's so incredibly massive that it can afford to be patient, as it keeps the temperature and pressure up. Even if the odds of any two protons fusing during a collision are astronomically low, the sun has octillions of them packed together under immense pressure. It succeeds through sheer volume, not intensity. If you had a cubic meter of the sun's core sitting in your backyard, it would only produce about 275 watts of fusion power, roughly the same as a few old-fashioned incandescent light bulbs. Now, the sun's core has a higher power-to-mass ratio than the sun as a whole, so if you had a cubic meter of the sun's core sitting in your backyard, it would produce more than the sun's average power-to-mass ratio, but still only 275 watts of fusion power, roughly the same as a few old-fashioned incandescent light bulbs, though it would give off far more from sheer heat as it cooled and ended the fusion process. Regardless, that is a power-to-mass ratio that would be fairly useless in a power plant. Even if we took to much larger stars, the math doesn't improve enough for our purposes. Stars range in mass from tiny red dwarfs to massive giants only a few hundred times heavier than them, yet their brightness, their fusion intensity, can vary by a factor of billions. In those massive stars, gravity forces fusion to happen much faster, but even they still take millions of years to burn through their fuel. They are still slow by human engineering standards, though this might barely be in the viable range, especially using deuterium, which fuses much easier, so much so that in brown dwarfs, so-called failed stars, they are relatively bright in the early days as they do undergo deuterium fusion, but they don't have much so they quickly run out, though quickly is still many millions of years, making them potentially useful. See our episode Colonizing Brown Dwarfs for more discussion of that. On Earth, we don't have gravity on our side, we certainly don't have millions of years. We can't build a reactor the size of a star. We have to build one that fits inside a building and justifies its billion-dollar price tag by producing massive amounts of energy right now. This is the heart of the Tokamak problem. To make a practical reactor, we have to make our fuel fuse millions of times faster than it does in the sun. That means we can't stop at 15 million degrees. To get reaction rates we need, we have to aim for 150 million degrees, 10 times hotter than the center of the sun, or better, even higher. We have to create conditions more violent than the heart of almost any star in the galaxy. We aren't just trying to bottle a star, we're trying to build a supersun in a box that runs on deuterium. And as it turns out, building a box that can hold a supersun without melting is the hardest part. Quantum tunneling, winning by statistics, not strength. So far, this all sounds impossible. If atomic nuclei repel each other so strongly, and the strong nuclear force only works once they're practically touching, then brute force alone should not be enough. Even at enormous temperatures, most nuclei simply don't have the energy needed to cross the Coulomb barrier. They should bounce off forever. In a purely classical universe, they would. Fusion happens at all, whether in stars or reactors, because the universe is not purely classical. At very small scales, particles don't behave like solid objects with exact positions and exact energies. They behave like probability distributions. Their energy, position, and momentum are all real, but fuzzy, with unavoidable uncertainty baked in. That uncertainty is not a rounding error, it's the entire loophole. This is what we call quantum tunneling. Instead of thinking in terms of particles either having enough energy or not enough, it's more accurate to think in terms of likelihood. A nucleus might need the equivalent of 10 units of energy to cross the Coulomb barrier. If it only has 9, classical physics says that's a hard no. But quantum mechanics says something different. That 9 comes with a small but non-zero chance of behaving like 10. An 8 has a smaller chance. A 7 has a much smaller one still. But even a 1 has a chance. Even if it's so small it might take eons to happen even once in the whole universe. That's how iron stars might come into existence 10 to the 1500 years from now. Most of fusion in modern stars happens with 8s and 7s, not 10s. That means almost every collision fails. Nuclei slam together, repel, scatter, and fly apart again. But once in a while, very rarely, the uncertainties line up just right. A particle that shouldn't quite make it does. When that happens, the nuclei get close enough for the strong nuclear force to take over, snap them together, and release energy. So they don't push through the barrier so much as slip past it. This is not common. It is not efficient. But it's not zero. That's all fusion needs. Temperature still matters enormously because higher temperatures mean faster particles and more collisions. But temperature alone isn't enough. Fusion is a statistical process. You need vast numbers of particles colliding again and again for those rare successful events to add up to anything useful. In fact, far more collisions fail than most people realize. One reason we prefer deuterium over regular hydrogen for fusion fuel is because it has a lower Coulomb barrier. The other is because protons ramming into each other as basic hydrogen tend not to stick together, wasting the entire event. When two protons ram into each other, they typically form a short-lived diproton and then fall back apart. But while they're briefly merged, there's a tiny chance that something more dramatic happens. A change inside that 6-quark jumble converts one proton into a neutron. When that occurs, what's left behind is deuterium. A proton and neutron bound together, with a positron, the antimatter counterpart of the electron, spat out in the process. You can think of this like two people jogging past each other and clapping hands as they pass. Most of the time, nothing special happens. For a brief moment they merge unstably, but there's a finite chance that lightning strikes at that exact moment, leaving them fused together as something new. That is essentially how proton-proton fusion works in stars. Most encounters go nowhere. Very rarely, everything lines up just right, and those rare successes are what keep stars shining, slowly and patiently. However, on Earth, we can't wait for the lightning to strike to turn a proton into a neutron. That's why we use fuel like deuterium and tritium, isotopes of hydrogen that come with those neutrons already pre-installed. It lowers the bar, but even with preloaded fuel, we are still playing a game of cosmic statistics. Quantum tunneling makes fusion possible, it just doesn't make it easy. And that brings us to the next problem, which has much less to do with nuclear physics and much more to do with engineering. Holding the fire, the plasma problem. If fusion were just about reaching extreme temperatures, we could at least imagine brute forcing our way there. Heat something up enough, insulate it well, and wait. But fusion fuel isn't a solid, a liquid, or even a normal gas. At fusion temperatures, atoms are ripped apart into plasma, a roiling mix of baronuclei and free electrons, all moving at enormous speeds. Plasma does not behave politely. It conducts electricity, generates its own magnetic fields, and reacts violently to even tiny disturbances. And most importantly, plasma cannot touch anything solid. I mean, it can, but so can a lightsaber. The solid simply stops being solid at that point. This isn't even basic plasma either. We're operating at 1,000 times faster and 1,000,000 times more energetically than the stuff in a neon sign or a lightning bolt. If the plasma touches the wall vaporizes, the plasma cools instantly, and the reaction stops. Game over. So the core engineering challenge of fusion isn't about how just to light that fire up, it's how to hold it without touching it. The only practical tool we have for that job is magnetism. Because plasma is made of charged particles, it responds strongly to magnetic fields. Charged particles spiral along magnetic field lines, which mean magnetic fields can act like invisible walls. You cannot put plasma in a box, but you can persuade it to stay inside a magnetic cage. In principle. In practice, plasma does everything it can to escape. Magnetic fields must be shaped, tuned, and constantly adjusted to keep plasma from writhing, wobbling, and developing instabilities. Tiny imperfections grow. Small ripples become violent motions. Heat leaks away through turbulence, and the hotter and denser plasma gets, the harder it becomes to control. Magnetism is also hard to work with, unlike electric fields, because magnetic fields are not easily blocked, and to make it worse, our best paths to really awesome magnetic fields tend to involve superconductors, who do not work at earthly temperatures either, but in the opposite, frigid direction. This is why fusion reactors are not passive machines. They are active systems, continuously correcting and compensating for plasma behavior that wants very badly to go wrong. And this is where the geometry starts to matter. If you try to confine plasma in a straight magnetic tube, it simply escapes out the ends. To trap it for long enough to matter, the magnetic field has to loop back in on itself. The simplest way to do that is to bend the chamber around into a ring, a torus or donut, and wrap magnetic fields around it. The basic idea leads directly to the Tokamak. Tokamaks are not built because they are elegant or easy. They exist because they solve several problems at once: closing the magnetic bubble, stabilizing plasma motion, and allowing the fuel to circulate long enough for fusion to occur. And this brings us to the name Tokamak, which, if you're curious, is just an abridgment of the Russian words for toroidal chamber with magnets. The other approaches I mentioned earlier, the stellarator and the Z-pinch, are equally literal. Stellarator means star maker, and Z-pinch describes a plasma compressed by its own magnetic field. The Z-pinch is actually the simplest. It just tries to crush the plasma into a line. But it turns out that when you squeeze a plasma that hard, it tries to squirm out of your grip like a wet bar of soap. It's so unstable that it usually breaks apart before any real fusion can happen, though there have been improvements, and one day they might get their own episodes. And they have all similar issues and typically solve those problems by introducing new ones. Stronger magnetic fields mean more stress. Better confinement means more violent instabilities when things go wrong. Larger machines help, but they are expensive, complex, and unforgiving. For the same reasons, we don't just set off H-bombs, a large domed lake, to superheat water for a turbine. If your fusion reactor needs to be bigger than a city it would power, you got problems. And remember, we can always just beam energy down as microwaves from solar collectors in space, getting power from the giant fusion reactor we orbit. It's not about if we can make fusion work, again we already have, it's making it work economically. A city-sized reactor probably is not. This is the heart of the Tokamak problem. Fusion is not about reaching extreme conditions, it's about maintaining them, controlling them, and doing so reliably, over and over again, in a machine that has to operate like infrastructure rather than experiment. And once we understand that, we can finally talk about what Tokamaks actually do well and where they struggle. What Tokamaks actually solved. It's easy to look at Fusion's long timeline and conclude that nothing has really changed, but the impression mostly comes from watching the finish line, not the distance covered. Early Tokamaks struggled to confine plasma at all. In the 1960s and early 70s, keeping plasma stable for even a fraction of a second was considered progress. Instabilities toward the plasma part almost as soon as it formed. Heat leaked away faster than it could be added. Fusion temperatures were a goal, not a reality. Over time that changed, slowly and at great expense. Magnetic field shaping improved. Plasma cross-sections evolved from simple circles into carefully sculpted forms that reduced turbulence. Heating methods improved, from simple ohmic heating to powerful neutral beam injectors and radio frequency systems that could selectively energize different parts of the plasma. Control systems got faster and smarter, correcting instabilities before they cascaded. Taken together, it ended up in something very important. Confinement improved by orders of magnitude. Temperatures climbed from a few million degrees to tens of millions, and then past 100 million. Plasma lifetime stretched from milliseconds to seconds, eventually to minutes. In the industry, they measure this using the triple product, a single number that combines how hot the plasma is, how dense it is, and how long we can keep it contained. If you plot that number over the last 50 years, the curve is astonishing. It has actually outpaced Moore's law for much of its history. Bluntly, we are now thousands of times better at fusion than the machines we started with. Rolling our eyes and saying fusion never progresses or that's gone nowhere, when we are literally orders of magnitudes beyond the era that managed to make hydrogen bombs work, is not rational skepticism. It's just ignoring the scale of the problem we're actually trying to solve, which again is star-sized. We have not been standing still. We've been climbing a mountain that turned out to be much taller than we first thought. Anyway, by the 1990s, Tokamaks had crossed a psychological threshold. Facilities like JET in the United Kingdom demonstrated deuterium-tritium fusion producing megawatts of power. More recently, JET sustained a fusion burn that released 59 megajoules of energy over 5 seconds. That result did not power a city, it's akin to a gallon of gasoline, but it proved something far more important. Fusion plasmas could be hot, dense, and stable at the same time. That was never guaranteed. Tokamaks didn't solve fusion, but they did solve enough of the physics to reveal where real bottlenecks actually are at. And once confinement stopped being the main question, a harder one took its place. The Tokamak problem precisely stated. So what exactly is the Tokamak problem today? It isn't that fusion reactions won't happen. They do. It isn't that plasmas can't be confined. They can. Modern Tokamaks routinely reach fusion temperatures and hold plasma long enough for sustained reactions to occur. The problem is that none of this automatically translates into a useful power plant. A Tokamak can produce fusion energy while still consuming more energy overall than it delivers as electricity. Heating the plasma, running massive superconducting magnets, powering cooling system, and operating complex control hardware all takes energy. Fusion neutrons carry about 80% of the reaction energy, but capturing that energy efficiently, without destroying the reactor in the process, is far harder than it sounds. There is a fundamental irony here. Those neutrons are the product, but they're also the poison. They carry the very energy we want to harvest, but as they fly out of the plasma, they slam the reactor walls like a subatomic sledgehammer. They don't just make materials radioactive, a process called activation. They physically rearrange atoms of the structure itself. They create tiny bubbles of gas and knock atoms out of their crystal lattice, turning tough, high-tech, and often expensive alloys into something as brittle as glass. This means that as we get better at fusion, the environment inside the reactor becomes exponentially harsher. It leads to a cycle of downtime, maintenance, and replacement that none of our current designs scale particularly well. A power plant can't just operate in heroic bursts of a few seconds or minutes. It has to run day and night for years. Currently, our best experimental runs are still just brief interruptions compared to the relentless demands of a city's power grid. So the Tokamak problem isn't about whether fusion works, it's about whether we can turn a device that occasionally produces impressive fusion results into one that produces electricity steadily, predictably, and cheaply enough to matter. It's about economics as much as physics, and engineering as much as either. Fusion has crossed the line, though, from impossible to difficult. But difficult problems don't disappear just on their own. They demand clarity about what success actually looks like, and honesty about which approaches are getting us closer and which ones are simply getting bigger. And that brings us to the most famous Tokamak of all and the limits of scaling our way out of trouble. ITER and the limits of scaling. And all of this brings us inevitably to ITER. ITER is often described as the fusion reactor, the machine that will finally prove fusion works. That description is understandable, but it's also misleading. ITER is not designed to power cities. It won't generate electricity for the grid. It won't continuously run a power plant. ITER's job is far narrower and far more important than that. ITER exists to answer a very specific question. What happens to Tokamak when you scale it up to near power plant size? Up to now, fusion research has lived in a difficult middle ground. Small machines are easier to build and cheaper to operate, and easier to get Congress to fund, but they leak heat and particles too quickly to behave like real reactors. Large machines confine plasma better, but they bring new problems: mechanical stress, material damage, control complexity, and sheer cost. ITER is the experiment that pushes through that boundary. Its goal is to demonstrate a fusion gain factor, what physicists call Q, of about 10. That means producing 10 times more fusion power in the plasma than the energy injected to heat it. Not 10 times more electricity, not net grid power, just proof that at scale, plasma physics behaves the way all models say it should. That may sound underwhelming, but it really isn't. Crossing that threshold matters because confinement improves with size. Bigger plasmas cool more slowly. Turbulence behaves differently. Certain instabilities become easier to manage. For decades, theory has said this should happen, but ITER is the first machine large enough to test it directly. At the same time, ITER will expose the other half of the problem. A reactor that produces enormous fusion power inside the plasma is still useless if everything around that plasma falls apart. High-energy neutrons will slam into the reactor walls, damaging materials, degrading superconducting magnets, and activating components. Heat has to be extracted efficiently without destroying the structure meant to collect it. Maintenance has to be possible without shutting the whole system down for years at a time. So ITER will not solve these problems, but will tell us unmistakably how bad they really are. That's the point. Scaling up does not magically turn fusion to a power plant. It does is strip away uncertainty. It tells us whether the remaining obstacles are engineering problems or fundamental roadblocks. Fusion is one of those ideas that always feels just within reach, but never quite arrives. If you enjoy digging into why technologies succeed or stall, check out Tech Alter, where Martin breaks down the business and engineering realities behind modern tech. And energy is not just convenience, it is survival. A reliable high-output source like fusion could mean the difference between collapse and continuity during something like a new ice age. That's exactly what I explore in my exclusive, Surviving a New Ice Age, where we look at how civilization adapts when the environment turns hostile, and what technologies make that possible. You can find that in every episode of SFIA early and ad-free on Nebula, along with several years of our monthly exclusive episodes and other bonus content and extended editions, not to mention hundreds of other awesome creators. Right now, Nebula is offering 40% off lifetime access, just $300 for permanent access to everything on the platform. Use my link or the QR code to get that deal, and there's also 50% off an annual plan. That's just $30 for the whole year. What about other approaches? At this point, it's fair to ask whether Tokamaks are the only game in town. They are not. Stellarators, for example, trade operational simplicity for geometric complexity. They can, in principle, confine plasma continuously without the pulsed currents Tokamaks rely on, at the cost of extremely intricate magnetic shapes. Modern stellarators are far better than their early predecessors, and they may yet prove better suited to steady operation. Inertial confinement, using lasers to crush tiny fuel pellets, has made dramatic progress as well, particularly in the last few years, but it faces its own scaling challenges, especially when it comes to repetition rate, efficiency, and turning brief bursts into continuous power. And then there's the growing ecosystem of private fusion startups, exploring everything from compact tokamaks to magnetized target fusion to approaches that barely resemble reactors at all. Some of these ideas may work, some won't, most will fail quietly, some will probably be scams run by criminals. With the exception of those, all will be criminally underfunded in my opinion. And again, we probably ought to give these less well-known candidates a deeper look, but what matters today is that none of these approaches escape the same fundamental constraints. They all have to produce energy faster than they consume it. They all have to survive their own neutron flux. They all have to operate reliably, maintainably, and cheaply enough to compete with other ways of generating power. There are many paths forward, none of them are shortcuts. So, where does that leave fusion? Fusion today sits in a strange but important place. It is no longer science fiction, no longer a purely theoretical exercise, and no longer an unsolved physics problem, but is also not yet infrastructure. As we said, fusion has crossed the line from impossible to difficult, and difficult problems don't yield to slogans or timelines. They yield to iteration, scale testing, and brutal honesty about costs and trade-offs. They are stubborn, but then so are we. It doesn't care how badly we want it to work, of course. It demands results at full scale, under real-world conditions for years at a time. If fusion ever becomes a practical power source, it won't arrive as a sudden revolution. It will arrive quietly, after decades of machines that didn't quite work, followed by one that finally did, and then a generation of engineers whose job it is to make it boring to everyone except investors. And other engineers, of course. If it never quite gets there, we won't be left empty-handed. Fusion research has already driven advances in superconductors, plasma physics, material sciences, and high-power control systems that spill over into countless other technologies. So the right way to think about fusion isn't as a promise waiting to be fulfilled, or a failure waiting to be admitted. It's an ongoing test of how far controlled engineering can be pushed against the most extreme forces we know how to create. We are not bottling a star. We're asking whether we can build a machine that does something even harder, and whether it's worth the price of finding out. And when the journey keeps paying dividends, and the destination is effectively limitless clean energy, I'd say the answer is as clear and obvious as the sun itself.